Hello, I'm Olivetti, and this talk will be about a tool, a computer program called round eliminator that can be used to automatically obtain lower and upper bounds in the distributed setting. This tool gives a way to automatically apply the round elimination technique, that is a technique that has been used in the last years to prove many interesting lower bounds. So let's see how we can prove lower bounds with this technique. Let's say that we want to prove a lower bound for some problem P0. A requirement of this technique is that P0 must be a locally checkable problem, meaning that we can describe P0 by just stating its local constraints. We start from P0 and we try to define a family of problems, P1, P2, P3 and so on, such that for any I, Pi plus 1 is at least one round easier than Pi. If we are able to prove that there exists a family containing T of such problems, such that the last problem of the family is not 0 round solvable, we directly get a lower bound of T plus 1 rounds for the original problem. In fact, if Pt requires at least one round, it implies that Pt minus 1 requires at least 2 rounds, and by repeating the same reasoning, we get that P0 requires at least T plus 1 rounds. The hard part in applying this technique is to find this family of problems that satisfies this property, that is, each problem is at least one round easier than the previous one. A good news is that from last year, we know that such family can, in theory, be defined automatically. In fact, given the description of Pi, we can generate mechanically the description of Pi plus 1, a problem that is exactly one round easier. The bad news is that such description could be exponentially larger than the description of Pi. A way that we have to solve this issue is to try to simplify the description of the problem to make it much smaller. And the hard part in doing that is that while we want to reduce the description complexity of the problem, we do not want that the time complexity of the problem becomes much smaller. Because if the problem gets too easy, we cannot repeat this process for many steps and get a good lower bound. While the fact that this family of problems can be defined automatically is a news from last year, notice that the round elimination technique itself is not new. In fact, we can see the lineal lower bound for 3-coloring cycle as an application of this technique. In fact, the proof essentially shows that if C coloring can be solved in T rounds, then 2 to the C coloring can be solved in at most T minus 1 rounds. If we apply this reasoning enough times, we get some coloring variant that can be solved in 0 rounds. But if we start with a small enough T at the beginning, we can show that this implies a contradiction. So let's now see what is round eliminator. Round eliminator is a tool that automatizes the process of finding the family of problems that we get through round elimination. This tool is open source, the code is on GitHub, and you can try it directly in your browser, even from your phone. What we can do with this tool is the following. We just type the description of our favorite problem using some specific language, and then we can just ask round eliminator to find lower and upper bounds for us. What the program does is to apply the round elimination technique to generate a family of problems by also trying to find good simplifications that can be used to reduce the size of the intermediate problems without altering their complexity too much. So let's see some examples. Let's start by seeing how to encode problems. And let's take as example the Sinkless orientation problem. In this problem, we have a graph, and we want to orient edges such that every node has at least one outgoing edge. So a solution looks like this one. In order to use the round eliminator program, we have to describe this problem by using local constraints. In particular, we require nodes to write a label on each incident half edge, and we have to list the allowed node and edge configurations. Since we want edges to be oriented, we consider two labels, H and T, heads and tails, and we require each node to write on each edge if it is oriented outgoing with T or incoming with H. So let's see what are the constraints. Let's start from the edges, that is the easier case. Edges must be properly oriented, so if a node from one side writes H, the node on the other side must write T, and vice versa. So the only allowed edge configuration is TH. Let's now see the node's constraints. Each node must have at least one outgoing edge, hence each allowed configuration must contain at least one T. Hence, if for example delta is 3, we get that the allowed configurations are TTT, TTH, and THH, so at least one T. And note that the order is not important. If we now give such constraints to the round eliminator and we press speed up a few times, we get the following. The speed up button generates at each step the next problem of the family, and if we continue for enough steps, we can notice that we get the following. We get a problem that can be described with ABB as node constraints and BAB as edge constraints, that stands for BA or BB, and if we look at 2 steps before, we have the same problem, ABB, BAB. This is an example of so-called fixed point. And from the theory side, we know that a fixed point directly implies an omega log n deterministic lower bound and omega log n randomized lower bound. Note that we already knew such lower bounds for the Sinkless orientation problem from 2016. But this shows that what 4 years ago required pages and pages of hard proofs, now it can be entirely automated. Let's now see an additional example. Let's consider the bipartite maximal matching problem. For the Sinkless orientation problem, we had a label for each half edge, while this time we have a single label on each edge. I'm not going to discuss the reason in detail, but the high-level idea is that in general, we can encode constraints over nodes and hyperedges, where each node has to output a label over each incident hyperedge. And then we can represent a hypergraph using a bipartite two-color graph. And this basically means that we can also define problems over bipartite two-color graphs, where now we have a single label on each edge. So let's see how to encode bipartite maximal matching. We are going to use 3 labels. The first 2 are very intuitive. An edge is either in the matching, and it is labeled M, or it is not in the matching, and it is labeled O. Unfortunately, we need a third label in order to encode maximality, and we require white unmatched nodes to point with the label P to matched black nodes. One can prove that for maximal matching, 3 labels are actually required, and that these constraints correctly encode the maximal matching problem. So let's see what happens if we give this problem to the round eliminator program, in the case where delta is 5. Again, we can press speed up a few times. This time we can see that, unfortunately, differently from Sinkless orientation, the size of the problems that we get grows more and more at each step. And this makes it hard to prove a lower bound for this problem. But we can try a different approach. Let's start from scratch and let's ask round eliminator to find a lower bound for us. This is what we get. Lower bound of 9 rounds. We can see that the program performed round elimination for multiple steps and performed some simplifications at each step to keep the description of the intermediate problems small. So in this way, we obtain a family of problems that can be described in a compact way. Now let's try to see if such bound is tight. Let's ask the program to find an upper bound for us. This is what we get, upper bound of 9 rounds. So the program is telling us that bipartite maximal matching, if delta is 5, requires exactly 9 rounds. This does not directly give lower and upper bounds for maximal matching, but only lower and upper bounds for a specific value of delta that is 5. And what we need to do is to see the simplifications that round eliminator did and try to generalize the procedure for all values of delta. Now the good thing is that if the number of labels is small at each step, then this becomes doable. Finally, note that there are more features of the round eliminator that one can try, and a full tutorial with plenty of examples can be found on GitHub. So let's conclude with some open questions. First of all, as we have seen, the intermediate problems that we get while proving lower bounds tend to have larger and larger size. So an important thing that we need to do is to reduce the size of the intermediate problems. In order to do so, we need to find good simplifications. That is, the description of the problem should get smaller, but the time complexity shouldn't reduce by much. What we don't know is when it's possible to have such simplifications. Also, it would be nice to be able to have some heuristic that given a simplification, it tells us if it's good or not. Then another open question regards coloring problems. For such problems, it really seems that the growth in the description complexity of the problems is fully exponential. And it seems that if we try to perform any kind of simplification, we don't get anything useful. So maybe finding a compact way to describe the intermediate problems could be useful. And that's it. Thanks for listening.